Welcome back on our continuing journey in the land of fluids. A question comes up, you've ever tried this, put an object underwater and it feels like it doesn't weigh as much, so as you submerge it or whatever, you feel this force kind of lifting it, actually helping you pick it up. If you use a beach ball, for example, and try to push it under the water, that force is very strong. You try to push that beach ball down, doesn't it want to pop back up again? It's very hard to hold those under the water. A lot of things are like this, pool noodles, etc., etc. Don't they have a tendency to float? There's a force when we start to put things into fluids, and this force, of course, is known as buoyancy. So buoyancy is that tendency for objects to pop back up to the surface. The question is, where does that come from? So let's take a look at the forces actually on an object. So let's say we put something underneath the water. So here's the water itself, and we push it up underneath the water itself. So now it's down below the surface. So if we look at the forces themselves, actually acting on this, isn't there a pressure pushing down on the top of this can? Let's say it's just a can. And so there's pressure from the water pushing down from up above. And isn't there also pressure on the bottom of the can pushing back up? So if we look at those pressures, the pressures themselves are different. The pressure here on the top of the can is less than the pressure on the bottom because the bottom of the can is actually deeper into the water and farther down. And we know that the pressures, for example, P1 here is going to be equal to our new friend in our new formula, rho GH. And I'll call that H1. H1 is the depth of the water. So H1 is how far it is from the surface of the water to the top of the can itself. P2 has a depth of H2 from the surface of the water down to where the base of the can is, and we'll call that H2. And this pressure at the bottom here is, call it P2, is going to be rho, the density of the water, G times H2. So that has a pressure of this. And notice H2 is larger than H1, so the pressure obviously is greater there. But let's look at this in terms of the forces themselves. So if we take a look at forces, we know that pressure is equal to the force divided by the area. All right, now we look at the area. The area of what? Well, it's the area that the pressure is acting on. So we're going to call this A1, which is the top of the can. That's where the pressure is being pressed on that top of the can. And at the bottom, we're going to call that one A2. So if we look here, the force on the top of the can we'll call F1. The pressure is P1, and then this is A1. So let's solve this for the force. The force on the top of the can, F1, is going to be equal to P1 times A1. So let's put this in the formula itself. The force here, F1 on the top of the can, is going to be equal to, well, instead of writing P1, can I write rho GH1 times the area, top of the can is A1. All right, now, that takes care of the top of the can itself and the pressure that's on that. All right, now, let's look at the bottom of the can. Well, of course, the pressure on the bottom of the can, P2, is going to be equal to F2 divided by A2. Solving this for the force, once again, we have F2 is equal to P2 times A2. All right, and voila, can we substitute in here to find the force here? F2 is going to be equal to rho GH2 times the area. The area of what? The bottom of the can. So if we look here, we've got ourselves two formulas that tell us what the forces are actually acting on this part of the can. Now, one thing to note. Let's take a look at the pressure acting on the sides of the can. So if I have a pressure pushing on from this side at that particular depth, on the sides of the can, isn't there another one on the opposite side as well? We learned this in the previous lesson. And if the pressure is pushing on this side of the can, isn't there another pressure pushing exactly on the opposite side? So the pressures on the x direction on the left and on the right will equal each other out. Not so for the pressures on the top of the can and the bottom of the can. We recognize the fact that the pressure, P2, is larger than P1, so therefore the force, F2, must be larger than F1.